Hello everyone, we are team Quadruple and our teammates are Ashwin Pathak, Ayush Rai, Harshit Mahajan and Vidit Jain. The topics we are covering in this project are number fields and the biography of George Cantor and Bertrand's postulates and its applications. So the prerequisites for understanding our projects are number theory, field and vectors, set theory, prime numbers, Lucas-Lehmann test, Chebyshev theorem, incongruent moduli. Okay guys, today we will learn about the topic named as number fields. Before we directly run into topic number fields, first we have to clear some topics like ring, fields and vectors. Okay, so let's start with the definition of a ring. Ring is a set of numbers where you can add, subtract as well as multiply, but not divide. Keep this in mind, not divide. In case of addition, it follows both properties, distributive as well as commutative. But in case of multiplication, it's only distributive, not commutative. So let's take a basic example of a ring. Let's consider a 2 by 2 matrix of real numbers. Here ABCD, where ABCD are real numbers. Here you can add, which is distributive as well as commutative. But in case of multiplication, it is just distributive, not commutative. So it's a ring. So on an overall note of ring, what happens in the ring just stays in the ring. Okay. Now a field. Field is just a slight extension of rings where you can add, multiply, divide, subtract, and where both addition and subtraction are both distributive and commutative. So example of fields are rational numbers, real numbers, and as well as complex numbers. Last but not the least, vectors. Vectors can be thought of as consisting of sequence or tuples where x1, x2, x3 whose entries are x1, x2, x3s. Where if you want to add two tuples or sequence, you can just add like this. Here, let's say vector 1 is x1, x2, x dash till xn, and another vector is x1 dash, x2 dash till xn. So if you want to add them, you can directly add one by one element of each, like x1 plus x1 dash, x2 plus x2 dash, and so on. So this is a brief intros of ring, fields and vectors. Okay. So let's talk about number fields now. Let's start with its definition. An algebraic number field f is a finite degree field extension of the field of rational numbers q. Thus f is a field that contains q and has finite dimension when considered as a vector space over q. So now we will talk about two basic fields like quadratic fields and cyclomatic fields. Let's start with quadratic fields. For any square-free integer d, the quadratic field q of root d is a number field obtained by adjoining the square roots of d to the fields of rational numbers. Arithmetic operations in this field are defined in analogy with the case of Gaussian rational numbers where d is equals to -1. Now talk about cyclomatic fields where n is equals to e to the power 2 pi iota by n is a number field obtained by q by adjoining a primitive nth root of unity, which is represented by n. Okay. So now the question arises is why number fields? Historically, an important reason is that they allow us to factorize certain diaphonetic equations. For example, for general Dedekind rings, in particular rings of integers, there is a unique factorization of ideals into a product of prime ideals. For example, here is a Ramanujan equation where x square is equals to 2 power n minus 7 may be factorized as x plus root of minus 7 multiplied by x minus root of minus 7, which is equals to 2 power n. Okay, so the amazing unique factorization may be restored by embedding O of k into a larger set which consists of objects called ideals. There is a natural equivalence relation that one can place on these ideals, and the number of equivalence classes called the number classes and written as h of k is one of the most important invariant in number theory. In a certain sense, it measures the extent to which unique factorization fails in number fields k. Okay, now basis for number fields. First is integral basis. An integral basis for a natural field f of degree n is a set where b is equals to b1 to bn of n algebraic integers in F such that every element of the ring of integers F of F can be written uniquely as a Z linear combination of elements of B. That is, for any x in OF, we have x equals to m1 dot b1 plus m2 dot b2 till mn dot bn, where the mi are ordinary integers. Now talk about power bases. A number field f of degree n whose bases of the are of the form bx equals to 1x x square till x to the power n minus 1 for some element x belongs to f is called a power basis. There are two main properties of power bases: power integral bases as well as monogenic fields. So
I'm going to take you through the journey of the famous German mathematician Georg Cantor. He is known for discovering and building a hierarchy of infinite sets according to their cardinal numbers. He is also known for inventing the Cantor set, which is now a fundamental theory in mathematics. Born into a family of musicians, he displayed an aptitude for music at a young age. He also excelled in his studies and was peculiarly drawn towards mathematics. He received his education from the University of Berlin, where he specialized in physics, philosophy, and mathematics. Before embarking on a successful academic career, although Cantor's view on certain mathematical topics were severely opposed by many of his contemporaries, he refused to give into their criticism and continued his research. Apart from the cardinal numbers, George Cantor is also credited for having furthered the study of trigonometry and transfinite numbers. In addition, he established the importance of one-to-one correspondence in set theory. He suffered from mental illness during the later years of his life, yet he remained actively involved in mathematical works. Okay, so this was the introduction. Now coming to the career. George Cantor began his career by teaching in a Berlin girls' school for a brief period of time. He then accepted a position at University of Halle, where he spent his entire career. He joined as a lecturer in 1869 and was promoted to assistant professor in 1872 and full professor in 1879. He published a series of 10 papers from 1869 to 1873 in which he dealt with theory of numbers. A colleague, Heinrich Edward Hehn, recognized Cantor's capability and encouraged him to work on theory of trigonometric series. He started with the work performed on trigonometric series by German mathematician Bernhard Riemann a few years ago and extended it to show that the function of a complex variable can be represented in only one way by a trigonometric series. He began his work on what became later known as set theory in 1874. Cantor's correspondence with Richard Dedekind, mathematician at Brunswick Technical Institute, triggered in his mind on theory of sets. In 1874, he published an article on the poverty of the golden collection of all real algebraic numbers, which marked the beginning of set theory as a branch of mathematics. The article provided a rigorous proof that there was more than one kind of infinity. Through his work, he proved that real numbers are not countable. Extending his research, he published a series of 6 articles in Mathematische Annalen between 1879 and 1884 that performed an introduction to his set theory. He also introduced to the Cantor set during this time. During this time, he faced severe criticism of his work, which is believed to have affected his mental health, even though he continued his mathematical work despite the criticism. In 1891, he published a paper containing his diagonal argument for the existence of an uncountable set. He applied the same idea to prove now what is known as Cantor's theorem. The theorem states that for any set A, the set of all subsets of A has a strictly greater cardinality than A itself. By this time, his mental health had begun to deteriorate, though he still determinedly performed mathematical research. His last significant papers on set theory were published in 1895 and 1897 in Mathematische Annalen under Felix Klein's editorship. Okay. So these were his careers. Now coming to the major works. His major works were found that he founded the set theory, the branch of mathematical logic that studies set. This theory is most commonly applied to objects that are relevant to mathematics, though any type of object can be collected into a set. He also gave a new method of constructing transcendental numbers in 1874, which were first constructed by Joseph Liouville in 1844. Okay, so this was his major works. And now coming to the awards and achievements that he got. So he got the Royal Society Award. Uh, sorry, the Royal Society awarded Cantor its Sylvester Medal, the highest honor it can confer for works in mathematics in 1904. So these were his awards and achievements. Now he gave some very famous quotes. Some of the famous quotes are, "My beautiful proof lies all in ruins." Second, the essence of mathematics is in its freedom. Third, some infinities are bigger than other infinities. Okay, so this was George Cantor, the famous German mathematician. Okay, thank you.
Hi, I'm Ayush Rai, and today I'll be proving Bartran's postulate, which states that for a given x which is greater than 1, there exists a polynomial, a prime number p, such that it lies between x and 2x. So let's start with the proof of Bartran's postulate. So to prove Bartran's postulate, we'll be using few lemmas. So I'll start with the proof of these lemmas. So the lemma 1 states that for x greater than 1, let's assume that there is a function r of x such that x factorial in integral part of x factorial upon integral part of x factorial by 2 square, then this condition holds true, that is 2 power x minus 1 upon x plus 1 less than is equal to r of x, which is further less than is equal to 2 power x minus 1 upon into x plus 1. So the proof is, so if integral part of x is equal to 2k is even, then r of x is equal to 2k ck is the largest binomial coefficient in the expansion of 1 plus 1 2 power k. So 2 power 2k upon 2k plus 1 less than is equal to r of x, which is further less than is equal to 2 power 2k. That is 2 power 2k upon 2k plus 1 less than is equal to r of x less than is equal to 2 power 2k. I'll call this result as 1. Similarly, it can be proved for odd case also, which states that if integral part of 2x is 2k plus 1, then r of x is equal to 2k plus 1 ck into k plus 1. Now 2 into 2k plus 1 ck is equal to 2k plus 1 ck plus 2k plus 1 ck plus 1 less than is equal to 2 k power 2k plus 1. So the final result is 2 power 2k less than is equal to r of x less than is equal to 2 power 2k into k plus 1. So this is our lemma 1. Lemma 2 states that r of x less than is equal to 6 power x by 2 for all x greater than equal to 1. So we'll start with the proof of it. Say if x integral part of x is equal to 2 power k plus 1 is odd, then we need only to check that 2 power x 1 plus k by 2 less than is equal to 2 power x 1 plus 1 by 2 ki power k less than 6 power x by 2. The von Mangold function states that capital lambda of n, which I will call in this video as lambda of n is equal to log p if n is equal to p power k, where k is some integer greater than equal to 1, otherwise it's equal to 0. So the unique factorization property of the natural numbers implies that log of n equal to summation of capital lambda of d. Oh, so Bertrand's postulate proof. Let theta of x equal to sigma of log of p, where p less than is equal to x, where the sum is over primes p less than is equal to x. To prove Bertrand's postulate, it suffices to show that theta of x minus theta of x by 2 greater than 0 for any x greater than equal to 2. So Ramanujan stated that log of integral part of x factorial is equal to summation of log n, where n less than is equal to x is equal to sigma of log of capital lambda of d, de less than is equal to x, is equal to sigma of psi of x by e, where e less than is equal to x, where psi of x is equal to summation of capital lambda of n, n less than is equal to x. I'll call this result as 2. The above equation implies that log of x factorial, integral part of x factorial, minus 2 log of x by 2 integral part factorial is equal to psi of x minus psi of x by 2 plus psi of x by 3, and so on. Since the right hand side is an alternating side of a decreasing function, we deduce using the notion of the lemma that psi of x minus psi of x by 2 less than is equal to log of r of x, which is further less than is equal to psi of x minus psi of x by 2 plus psi of x by 3, which implies by lemma 2 that is psi of x minus psi of x by 2 less than is equal to x by 2 log 6. I'll call the previous result as 3 and this result as 4. Changing x to x by 2, comma x by 4, comma x by 8 in the above equation and adding up all the inequalities, we get psi of x less than x log 6. I'll call this result as 5. Then using 3 and lemma 1, which I stated before, we obtain x minus 1 log 2 minus log of x plus 1 less than is equal to psi of x minus psi of x by 2 plus psi of x by 3. Using 5 in the above inequality, we obtain psi of x minus psi of x by 2 greater than equal to x by 3 log 4 by 3 minus log 2 x plus 1. I'll call this result as 6. It is easy to see that the relation between the function psi and theta is given by psi of x is equal to theta of x plus theta power x by 2, theta of x power 1 by 2 plus theta of x power 1 by 3. I'll call this result as 7. So that psi of x minus 2 of psi of x power 1 by 2 is equal to theta of x minus theta of x power 1 by 2 plus theta of x power 1 by 3, and so on. So the right hand side is an alternating series of a decreasing function. We deduce as before that psi of x less than theta of x plus 2 psi x power 1 by 2. Now using 5 and the fact that psi of x less than is equal to psi of x, theta of x less than is equal to psi of x, we get psi of x minus psi of x by 2 less than is equal to theta of x plus 2 psi x power 1 by 2 minus theta of x power x by 2 less than theta of x minus theta of x by 2 plus 2 root x log 6. Using 6, we get with a equal to 1 by 3 log 4 by 3 and b equal to minus 2 log 6 and c is equal to minus log 2. That theta of x minus theta of x by 2 greater than ax plus b root x plus c minus log of x plus 1. We can write ax plus b root x plus c is equal to a of root x plus a into root x minus b, with a and b positive and b equal to 37.562. Thus for root x greater than b plus 1 by a equal to 47.98, we need only to check that e root x greater than 1 plus x. But this is evidently the case for x greater than 36, since e root x greater than 1 plus root x plus x by 2 plus x power 3 by 2 by 6. This establishes the result for x greater than 1151. For smaller values of x, we need only to observe that 2, 3, 5, 7, 13, 23, 43, 83 up to 1259 is a sequence of primes in which each member is less than twice its predecessor. From this, Bertrand's postulate is easily verified for x less than or equal to 1151. This completes the proof. So this was Ramanujan's proof of Bertrand's postulate. Thank you.
Let us see various applications of mathematics. We'll see these applications under number fields, discovery of George Cantor and Bertrand's postulate. We take each one by one. Number fields. First is primality test. Whether MP, which is a machine number, is a prime number or not. MP can be represented as 2 to the power p minus 1, where p is an odd number. Now we consider sequence. Si equals to 4 if I equals to 0, and Si minus 1 square minus 2 equals to Si otherwise. Now condition. MP is prime if and only if Sp minus 2 equals to 0 mod MP. Now we'll go to the proof. Sn equals to omega 2 to the power n plus omega bar 2 to the power n, where omega equals to 2 plus root 3 and omega bar equals to 2 minus root 3. Here we have written all the proof line by line, stating the sufficiency condition as well as the necessity condition, but we are omitting the proof due to the shortage of time. Here you can see that we have represented Sp minus 2 as in the form of omega and omega bar. Then we just use the contradiction method to prove NP is prime. In the necessity condition, we have used Legendre symbol and Euler's criterion, and we, using arithmetic operations and solving algebraic equations, we can reach to the conclusion that Sp minus 2 equals to 0 mod p. Hence, we have proved the necessity and sufficient conditions for MP to be prime. Thus, we can use number theory to prove MP is a prime number and test whether MP is a prime or not using the machine number. Number theory is the basis of constructing the codes. It is used for understanding the fundamental and logical sequences and properties of numbers. It seems very trivial now, but it surely was the landmark of its time. Now we'll see the discoveries of George Cantor. First is non-computable problems. He was able to compute the cardinalities of infinite sets using one-to-one correspondence mapping. Here we will see one-to-one mapping of various cardinalities of infinite sets. Now first consider the cardinality of the natural numbers and the cardinality of the integers. So 0 of the integer is mapped to 1, 1 is mapped to 2, minus 1 is mapped to 3, and so on. So we can map it as accordingly. N equals to 1 if z equals to 0, n equals to 2k where k is a natural number for z greater than 0, and n equals to 2k plus 1 for z less than 0. Hence we have obtained a one-to-one mapping. Similarly for n and n cross n, where n cross n is a tuple of n to n into n variables. So here we have we have used the process of diagonalization. Here we have written the numbers, and we can see that at each diagonal the sum is constant and the number of elements at each diagonal is 1 less than the sum. So we can reach to the n cross n formula by simply summating all the values less than the sum plus a, which is the value you want to reach. Hence, we have again obtained the one-to-one mapping. But for R and N, where R is the set of real numbers, we can also show that R01 is greater than set of natural numbers, where R01 represents numbers between 0 and 1. Hence, here each n can be represented as string of decimal digits which are real. So we can still find a real number which is not being mapped to any of the natural number. So here we have failed to obtain a one-to-one mapping. Thus, the cardinality of R is greater than the cardinality of n. Set theory algorithms. Set theory algorithms includes problems based on vector spaces and graphs. Set theory is an elementary part in the abstract algebra and discrete mathematics. It is a major area of research in science with many interrelated subfields. Now we'll see Bertrand's postulates. First is discriminator. Let us see about the discriminator function. Here the question is to determine the smallest value of k for a positive integer n such that 1 square, 2 square are all incongruent modulo k. So it is used for finding square roots of perfect squares. But the size of the number is not defined or not known. Hence take s equals to the set of 1 square, 2 square to the n square. Here we want to know what size of s is. We use discriminator function. Discriminator function is the minimum k such that 1 square, 2 square to the n square are all incongruent modulo k. Here we also consider another set dn which is shown as such. Now we use dn greater than equal to bn and bn greater than equal to dn. Hence we'll come out to the conclusion that dn equals to bn. All this is done is using Bertrand's postulates, which helps in finding the square roots of very large numbers in shorter time. Other algorithms include finding the sum such that the set 1, 2 to 2k can be arranged into k disjoint pairs so that the sum of the elements on each pair is a prime. These algorithms generally involve the set theory and arithmetics. These peculiar problems are basically proved by using Bertrand's weaker or stronger postulates. So these were all the applications. We are very grateful for providing us opportunities to present our mathematical concepts in this video. Thank you.